From Chapter 2 in your textbook, this screencast covers mixtures and pH. We're going to start our discussion by covering the following objective. Explain each term: mixture, solution, colloid, suspension, and emulsion. Mixtures consist of substances physically blended but not chemically combined. So for example, if we take water and mix sugar in with it, we get sugar water. Each of the initial substances, the water and the sugar, maintain their own chemical properties. Likewise, if we take sand and put it in water, we get sandy water. If we take salt and we put it in water, we get salt water. We get something that's wet and also tastes salty. Again, the components maintain their chemical properties. With mixtures, bonds are not being formed and bonds are not being broken. So we're not combining substances chemically. I want to contrast that to, say, a chemical reaction where we start with sodium and we start with chloride and then or chlorine rather, and then they form a ionic bond and the compound sodium chloride, which has its own properties that do not resemble sodium or chlorine. Why is it important to understand mixtures? Where our body fluids are basically complex mixtures of water and other molecules. Blood is basically 50% water and other molecules and cells mixed in it. You could say the same thing for lymph, and similarly for, say, cerebral spinal fluid. You have a mixture that is water and other substances mixed within it. Even if we talked about the intracellular fluid, that's fluid that's inside of cells, it's water with other substances such as proteins and amino acids mixed in it. As I mentioned, most mixtures in our bodies consist of molecules dissolved or suspended in water. Water content of the body ranges between 50 and 75% as a percentage of total body weight in general. Of course, this is going to depend on your age, your sex, your fat content. In general, as fat content as a percentage of body weight increases, water content as a percentage of body weight decreases. Mixtures have different names, or I should say there are different types of mixtures, and the type of mixture depends on the size and phase of the molecules that are mixed in water. Probably the mixture that people are most familiar with is a solution. And so I want to describe the components of the solution and then subsequently talk about the technical definition of a solution. So if we had a beaker of water and we dropped in, say, an Alka-Seltzer Plus, and it completely dissolved and we had a clear mixture after that, that would be a solution. Now, a solution has two components. You have the solvent, and in this example, it would be water because it's what's doing the dissolving. And then you have in solutions a solute, and the solute can be a gas, it can be a solid, it can be a liquid. In this case, it would be gases and solids, and it would be everything that was contained in that Alka-Seltzer Plus when it dissolved. So all of the ions, medicine, what have you that was in that Alka-Seltzer Plus, the carbon dioxide, all those would be solutes. Again, the solvent would be the water because it would be what's doing the dissolving. And the solvent and solute together, this mixture would be a solution. So what makes a mixture a solution? Well, it's defined as follows. The solute particles have to be very small, typically under 1 nanometer. That way they don't disperse light And so you have a mixture that is clear, as shown here with this copper sulfate solution. Also, they don't separate upon standing. So in other words, they'll remain dispersed in the solution. Over time, they won't settle out. That's the technical definition of a solution. In describing the concentration of a solution, we always express concentration in terms of the amount of solute in a unit of solution, not a unit of solvent, but a unit of solution. For example, we could describe normal saline in terms of percentage. So normal saline is 0.9%. That would be 0.9 grams of sodium chloride in 100 grams of solution. Again, not 100 grams of water, but 100 grams of solution. We can also describe concentration in terms of molarity. Normal saline is 0.154 molar. Molar means moles per liter. 1 mole of sodium chloride is 58.5 grams. Another type of mixture is called a colloid. Protein dissolved in milk would be an example of such a mixture. Here we have particles that are quite a bit larger than the solutes that we would see in a solution, and so they scatter light and the mixture is cloudy. However, they do stay permanently mixed. They don't fall out of the mixture over time. Most of the common colloids in the body are mixtures of protein and water. Again, an example would be milk. Another example would be the cytosol of cells. That's the fluid, the intracellular fluid inside of cells. Colloids can also undergo transitions from a liquid to a gel. For example, gelatin that you mix at room temperature and it's a liquid, and then you put it in the refrigerator, and if the temperature drops low enough, it turns into a gel. That would be another example of a colloid. And finally, we have suspensions. In suspensions, the particles in the mixture, like colloids, are large enough that they scatter light, so the mixture appears cloudy or opaque. But now the particles are so large that they will separate out over time. An example would be, as shown here, whole blood. If you were to take whole blood, withdraw whole blood from someone's vein using an anticoagulant so it doesn't clot, and place it in a test tube as shown here, over time those red blood cells would fall out of the mixture or separate upon standing. This, by the way, is also why many medicines tell you to shake well before using, because they are suspensions where certain components of the liquid medicines would fall to the bottom of the container. So to redisperse them, you shake. A special type of colloid is called an emulsion. This is where one liquid is mixed with another. An example of that would be the fat in breast milk. Breast milk, most of breast milk is water, but there is fat in breast milk that's mixed in. So breast milk would be an example of a emulsion. All right, so just to summarize what we discussed, a mixture is where we have different substances mixed together physically rather than chemically. And we retain the properties physical and chemical of what we mix together. For example, if we take salt and we take water, we get a mixture that is wet and salty. A solution is a mixture where the particles that are mixed in are small enough that they dissolve and they do not disperse light. So we have a clear, transparent mixture, and they also do not separate upon standing. With a colloid, the substances are larger, so they scatter light, so we get a mixture that is cloudy or opaque, and in some cases they can transition from a gel to a liquid or vice versa. However, these particles are small enough that they do not separate over time. With a suspension, again, the particles are large enough that they disperse light, so we get an opaque or cloudy mixture similar to a colloid. However, now the substances that are mixed in are large enough that they separate from the remainder of the mixture over time. And we said that a suspension where we have one liquid mixed in with another is called an emulsion. Let's now move on and discuss pH. Here are your learning objectives. Define acids and bases and explain what determines their strength. Explain the pH scale. Compare and contrast how acids, bases, and salts are all electrolytes. Explain how buffers function to resist changes in pH, and state the normal pH range for arterial blood and define acidosis or acidemia and alkalosis or alkalemia. Recall that water ionizes other molecules. Any salt, when placed in water, ionizes. So if we put sodium chloride in water, the sodium ions and chloride ions will be released. Similarly, if we put hydrogen chloride or hydrochloric acid into water, we would get hydrogen ions and chloride ions. Or if we took the strong base sodium hydroxide, placed it in water, we would get a separation of those ions into sodium ions and hydroxide ions. Let's define an acid and a base. An acid is a proton donor. That is, it releases hydrogen ions when placed in water. Now, let me explain the term proton donor. So hydrogen has an atomic number of 1. So when it forms a bond and it gives up the 1 electron that it has, the only thing that remains is a proton. So we refer to hydrogen ions when it comes to discussing acids and bases as a proton. So an acid, when it's placed in water, is a proton donor, or it releases hydrogen ions. A base is a proton acceptor. In other words, it accepts hydrogen ions, or it releases hydroxide ions in water, which will then accept the hydrogen ion and form water. So acids are proton donors, they release hydrogen ions. Bases are proton acceptors, they accept hydrogen ions. So acids are substances that when they ionize or dissociate in water, they release hydrogen ions. For example, if we took HCl, hydrogen chloride, and we added it to water, the hydrogen chloride would separate into hydrogen ions and chloride ions. Because it's releasing hydrogen ions, that makes it an acid. Common examples of acids would be lemon juice, vinegar, tomatoes, as well as coffee. So what's the difference between a strong acid and a weak acid? So here we have hydrogen chloride, and hydrogen chloride is a strong acid. Why is it a strong acid? Well, if you place hydrogen chloride in a beaker of water, pretty much all of it will dissociate, right? That is, the hydrogen and the chlorides will ionize, and so we'll have a large amount of hydrogen ions dispersed in the solution. And these hydrogen ions are very reactive. In other words, they will chemically react with other molecules. And those molecules could be your skin, your clothes, or other substances. That's why strong acids can give you a chemical burn, or why they can destroy metals and other substances around the house. Let's contrast that with a weak acid. What makes a weak acid a weak acid? Well, this is carbonic acid. If we were to place carbonic acid into a solution, most of it would remain carbonic acid. Only a small amount would actually ionize. So you'd only have a little hydrogen, a small concentration of hydrogen ions actually free roaming around in a solution. And that's why you can consume a weak acid like carbonic acid. And we do this all the time. Pretty much any carbonated beverage is a solution of carbonic acid, and we can consume it without any harm to our bodies because it's a weak acid. There's very few hydrogen ions roaming around to cause damage to our gastrointestinal tract or oral cavities. Now let's talk about bases. So we said bases are substances that when placed in water either take up hydrogen ions or they release hydroxide ions, which can then take up hydrogen ions. Common examples of bases are milk of magnesia, ammonia, as well as sodium hydroxide. Now, sodium hydroxide is a strong base, like hydrogen chloride is a strong acid, because if you place sodium hydroxide in solution, it pretty much completely dissociates into sodium ions and hydroxide ions. And like those hydrogen ions, these hydroxide ions are highly reactive. And so again, they can break bonds and form new bonds, and they don't really care if those molecules that of the bonds that they destroy are your skin or clothing or other substances. And that's why strong bases like strong acids can be damaging to the skin and other materials. A weak base is one that dissociates poorly when placed in water. So here we have sodium bicarbonate, which is baking soda. If we place that in water, most of it stays intact. Very little of it dissociates into sodium ions and bicarbonate ions, which can accept hydrogen ions. That's why sodium bicarbonate is a base. And that's why it's perfectly safe to place baking soda in toothpaste, for example. pH, which literally means potential of hydrogen, is a mathematical way to indicate the concentration of hydrogen ions in a solution. pH ranges from 0 to 14. pH below 7 is considered acidic, where the concentration of hydrogen ions, in this bracket means concentration, so the concentration of hydrogen ions is greater than the concentration of hydroxide ions. If we have a pH of 7 or above, I should say above 7, not 7 or above 7, it is basic, where there are more hydroxide ions than hydrogen ions. If we have a pH of 7, then the solution is neither basic or acidic. It is neutral, where the hydrogen ion concentration is equal to the hydroxide ion concentration. This image, which is from another book, shows the pH scale. So here we have water, which is pure water. So this is 100% H2O, which is neutral, where you have equal amounts of hydrogen ions and hydroxide ions. As we go from 7 toward 1, the concentration of hydrogen ions increases relative to hydroxide ions. And so as we go down the pH scale from 7 towards 0, there is an increase in acidity as the concentration of hydrogen ions increases. This is sometimes difficult for students to get into their heads, that as pH decreases, hydroxide ion concentration increases and acidity increases. And the pH scale is a logarithmic scale, which means that every unit is times 10. So something that is, say, has the pH of 4 is 10 times as acidic as something with a pH of 5. Something that is a pH of 3 is 100 times more acidic than something that with a pH of 5, because you have times 10, then you have times 10. A pH above 7 is basic, and as we move toward 14, it becomes more and more basic as the concentration of hydroxide ions relative to hydrogen ions increases. Why do we care about pH? Well, we'll get into the details of that eventually, but just note that blood pH has to be maintained, or what's normal blood pH in veins is in a very narrow range. Blood pH normally remains between 7.35 and 7.45. Notice that blood pH is not neutral. It is slightly basic. So we said that water, pure water, is neutral with the pH of 7. Why is water neutral? And again, we're talking pure water, not water with something mixed in it. Well, water ionizes slightly, not much, but slightly, where we actually have hydrogen ions and hydroxide ions released. But we have them released in equal concentration, therefore, pure water is neutral with a pH of 7. Because organisms are very sensitive to pH, they contain what are called buffers that help maintain pH within the normal range. Buffers work by taking up hydrogen ions when they are in excess and releasing hydrogen ions when there is a deficiency. So let's say what is normal in terms of pH is represented by these two hydrogen ions here. And here we have a buffer. So let's say there is a sudden increase in hydrogen ion concentration. So this is going to move pH down lower, down below the normal range. So we have a excess concentration of hydrogen ions. How does the buffer work? Well, in a situation where there's excess hydrogen ions, the buffer is going to come in and take up and pluck some of those hydrogen ions out of solution. So now we have a pH that is much closer to the normal range. It's not perfect, but it's much closer to the normal range than it otherwise would have been. Let's say in contrast, now there is a decrease in the concentration of hydrogen ions in solution. So now pH is increased above the normal range. So it's more basic than it should be. The buffer, in response to a deficiency in hydrogen ions, will release hydrogen ions in an attempt to return hydrogen ion concentration to the normal range. So this is how buffers work. They take up hydrogen ions when they are in excess, and they release hydrogen ions when the concentration is deficient. And in this way, they help maintain pH in the normal range. In addition to buffers, there are other mechanisms the human body has to control or regulate blood pH. The lungs and kidneys play very powerful roles in doing this. Lungs control the amount of carbon dioxide in the blood, which affects pH. Typically, as carbon dioxide levels rise in the blood, pH falls and vice versa. The kidneys are the most powerful regulators of blood pH because kidneys can remove less or more acids and bases from the blood into urine for removal from the body. pH of arterial blood is maintained between 7.35 and 7.45. That is the normal range. A pH below 7.35 is considered a acidosis, or one is said to have acidemia. A pH above 7.45, one is said to be in a state of alkalosis or alkalemia. Now let's review the learning objectives of the screencast. Explain each term: mixture, solution, colloid, suspension, and emulsion. For pH, define acids and bases and explain what determines their strength. Explain the pH scale. Compare and contrast how acids, bases, and salts are all electrolytes. Explain how buffers function to resist changes in pH. State the normal pH range for arterial blood and define acidosis or acidemia and alkalosis or alkalemia.